Hi folks, so the questions we have in front of us, guys, are the Section 8 questions from the DCG paper 2016 higher level, and these are the short answer questions from the Section 8 paper. 4 questions as always, and you have to do 3. Each question carries 20 marks, so 60 marks altogether. But what we're going to do is we're going to do all 4 of these questions on the page, working through them from A1 through to A4. So starting here with A1, which is a development question. So I'm going to zoom into that one there now. So for question A1, it says the images below show details of a curved metal shade from a set of traffic lights. So you can see here obviously the shade part of the traffic lights, and it's sitting over obviously the red, the yellow and the green. And it says the shade is based on a cylinder which is truncated and shaped as shown. So you can see here obviously it's a cylinder and it's obviously been cut, and then you can see it actually is cut in here obviously at a much more kind of acute angle as well. It says the drawing shows the circular end view. Okay, so we can see the end view over here, circular end view, and obviously you can see the bottom of it, so it's not a full circle, so you can see obviously that's the portion that's taken out here at the bottom. And the elevation of the shade, so we've got the elevation of the shade as well. The incomplete surface development of the shade has been projected beneath the elevation, so we have to, I assume we're going to have to complete this. So part A, complete the surface development, yep, and then part B, a point P, so you can see point P on the elevation here, on the surface of the cylinder is shown in the elevation. Locate this point in the end view and on the surface development. Okay. I'm going to tackle part A first there, the surface development. So usually when I'm doing developments, guys, I like to use labels. I find labels are very helpful. And as we can see here, the longest part, okay, of it, this bit, if you look over at the graphic over here, the longest point, okay, is out here at the front. So we can see that up here, okay. So that's that point right there. So these are technically generators that are running along it, and they all have different lengths, and they've already broken up for us. So I'm actually going to label this one. I'm actually just going to label it. I'm going to go use letters one side and I'm going to use numbers the other side, and I'll explain why in a while. But the very top one, I'm actually just going to go with 12. And the reason for that is like the clock. Okay, so if you think 12 was here, then I've got the 12 generator here as well. Okay, just so we can see that one there. And I'd have 12 here, just so you get the idea. So 12 is there, 12, 12, and you can see how far it came out to. Now on the left hand side, I'm actually going to go with letters. So I'll start with A to B and to C, and I'm just going to go down that far for now. And on this side I'm going to go with numbers 1 to 2 to 3. So if I was to project A across, just to show you there, if I was to project A across, and there, just move my laptop out of the way. If I was to project A across, you see that it would line up with 1. Okay, so just in relation to labeling, I can see then that when I'm looking from this direction, I'd have A on this side. So I'll just label, trying to keep this as neat as possible. So A would be there, 1 would be in the inside, then I'd have B and 2, then finally C and 3. Okay, so if I want to find them, as this folds out, I imagine, okay, it would kind of fold out where 12 is at the top, and we have 12 already here, okay, but I'd imagine 1, 2 and 3 would kind of go up like that, so it would kind of fold upwards. So if I was to bring it down here, I'm going to put, I'm just thinking now, and that would be, I'm just thinking there, A there, I should have written it the other way, sorry, so like A, B, and finally C, and then I have 1, 2, and 3, and we'll work on to the other sections in a second. Okay, so just to find those, simple bit of orthographic projection here. Okay, so I can see where 1 and A are already there. We've already got 1 and we've got A. So now it's to find 2 and B. So to find where 2 is, I'll project it down. And then it's very easy here, just a case of extend out B, and then likewise extend out 2. That'll give us points there, and the exact same then with 3 and C. Bring them down the whole way. So there we go. So that'll actually help us identify some further points. So that's the 1, That's where B is, and C, and likewise 2 and 3. Okay, so I'll do those curves in a minute now, and I'll extend them on. So that's going to be sketched. Now what I actually have to find, and if I was just to use labels again, this is why I use labels. Okay, I'm going to call this point here number 4, this one number 5, 6, obviously down to 7, and then obviously I've got D, E, F, and G. Okay, and what we're essentially going to have to do here, if I just use a compass, okay, now just to show you for 12 and 1, okay, essentially anytime you're doing development, it's very hard, you can't actually take the distance on a circumference, okay, you can't just measure that with your ruler or your set square, okay, so what we do is we take the closest accurate distance with that, and we mark that distance between 12 and 1, which would be the same as from 12 to A, or 1 to 2 and so on, so just make sure I have that exactly. And then what would have happened previously was 12 to 1 would have been marked off like that, okay, nice and easy. So we're going to do the exact same method. So now what I have done is I've already got the distance from 3 to 4. So it's a bit awkward here now, as in it's a very short distance. So on the compass this is a bit intricate work. So I've got that on my compass. So now from 3 I'm going to mark up there to 4. You can see that little mark there. Likewise, 3 to 4 will be the same as C to D. So I'll come down here to C. I'm going to mark it to D there. Okay, and I assume then the rest of these are the same. So D is the same. C to D is the same as D to E, E to F, and F to G. So I've got D. Down here is E. So C, D, E. Now I just have to find F. And likewise up here I would also have to find 3, 4, 5 into 6. Okay, so we have 6, and I would label all of them. So I've got D, E, F, and G, 3, 4, 5, 6, and 7. And that happens to make our life a little bit easier then. Now it's a case of projecting these across. So 4 will come across, and 4 is in line, as we can see there, with D. 5 is in line with E. 6 is in line with F, and then 7 and G. So once again, labels. So I'll go with my letters first. So D, E, F, G. Then I've got 4, 5, 6 and 7 as best I can there. So following the same steps as we did previously, I'm going to extend out. I can see that all these lines are a little bit short, so I'm just going to extend them out all a little bit further. And just realised I brought out the wrong one there. So there for my marks. So 3 is out, 1 way out, 4. I think that's about right. 5 needs to come out a little bit further. Then same with 6, and likewise with 7. Okay, so let's find the points. So 4 and D. There's 4. Keep it neat and tidy now. I'll just mark it down to D there. There's 5. Mark it down to E. There's 6. Mark it down to F. And finally 7. Mark it down to G. And as you can see there, it's simply a case now of heavying in our detail. The G line here is going to come out straight, likewise with the 7. And then it's a case of sketching in our curve. Okay, so we have, that is the surface development, so that's part A done. And now part B, it says a point P on the surface of the cylinder is shown in the elevation. Locate this point in the end view and on the surface development. Okay, this isn't too tricky, it's just a case of locating point P. So what we could do is we could create, as you can see here, if we just take the example of 1 and A here, okay, 1 and A, they are generators. So I can essentially create another generator there to run through the point P. And what that does is it helps me locate exactly where it is kind of along the line, the edge there. But if I was to bring that across, okay, here like that, now the issue we have here is it doesn't tell us, like let's say for example I just come down here to the picture, it doesn't tell us that P is there at this side, or it doesn't tell if it's at the opposite side. But for the sake of this, I'm going to imagine that it's maybe here at the front. Okay, so I'm going to put it out here on this side, in between the letters. Okay, in between the letters A and B. Okay, so you can see here it's in between the kind of the generators, A generator and B generator. Now you could also imagine that it is inside there as well, okay, but that would be obviously just depending on how you flip it, that could be at the back side. So essentially what I'm saying is though that P is going to be down here somewhere in between A and B. Okay, so first of all, just going to extend that down, because where it is in elevation has to be directly below that in our plan view of the development, and as I said previously, it was in between A and B, so it's inside this section here. And very simple here, all I'm going to do is, likewise where we took previously the distance from 12 to A, or 12 to 1, I'm now going to take the distance from A to B, or A to P in this case, which is in the direction of B. So I'm going to take that distance on my compass, which I've got, and from A, I'm going to mark it down. Hopefully you can see that in the video. There's a little mark there, and at that mark right there, I found it, that there is the positioning of my point P. Now depending on how you wanted to do it, technically it could also have been between 1 and 2, so it could have been from 1 in direction of 2. You could also debate that it's in this position here as well. Okay, but as I said, I'm taking it as in it was in this position, so I locate it down here in between the generators A and B. Okay, so just a little bit of understanding in that one there, guys. That's the surface development, guys. Question A1 done, completed. Now what we're going to do is we're going to move on to question A2 underneath it. Okay. So in this question here, guys, it says the image below shows a bar graph or presentation on a paper flip chart. The drawing on the right shows the plan and incomplete elevation of a similar bar graph and flip chart. Part A, complete the elevation of the flip chart and bar graph, and then part B, determine the true inclination of the diagonal AB to the horizontal plane. Okay, so part A first of all, and then we'll get on to part B, complete the elevation of the flip chart. So just coming over here, looking at it, we can obviously see that our flip chart, okay, looking at it here and kind of what they've given to us, it's obviously inclined to the horizontal plane, and it's also inclined to the vertical plane at a certain angle as well, but it's obviously up at an angle where it's resting on the ground. Okay, we can see it's sitting on the XY line, but then it's going up at a certain angle in relation to that. Now we don't know what that angle is. The only way to see that angle is obviously to look in along this edge here. It's not asking us for in that question, so we're going to start with part A anyway first. And first of all, we essentially have to complete the flip chart. So first of all, I'll just get in, you can see they've heavied in some of it first. So the top surface is here. I'm going to heavy that in at the top. Let's just use my T-square. That's the top surface there. And likewise with the side surface, which is this surface here, or this edge I should say, running down here. Okay, so there's that edge. And now what we essentially have to do is complete this kind of graph inside here. So they've already kind of completed the bottom line of the graph for us. You can see it extends up here and it extends up here. This green line A to B I assume is going to be helpful in a second. But the bit I'm going to find here first is how high this bit is going up here. So the kind of line running up along there. So I've already got the direction of it. So it's quite easy to complete that by extending this on parallel. And it's actually going to be parallel to this edge here. Okay, so just using a bit of sliding set squares there. Could have just extended on, but just want to be 100% accurate. Okay, so we've got that little bit in there. And now if we want to complete these kind of like little bar parts of the graph, what we can see is we have the line, the green line here, A to B, which is also represented in our elevation. We can see that it's going through, okay, kind of the opposite corners of each individual kind of bar. Well, it is going through the opposite one of the small one, but then it happens to go through the top one of the next bars in each one, you can see. So that'll actually determine the height for us of each one. So I suppose in that point then, what we have to note is that these lines here, okay, are all parallel to one another, like they are parallel to the edge here. So they'll actually run up parallel there. So it's actually simply a case of identifying all of these points here, okay, along this line here where the graph kind of starts. So they've given us the first one, which is right there. So we can find the next one by projecting up like that. Likewise with the third one, the fourth, the fifth, and luckily for us the sixth is already given to us. So to find the height of the first individual one, I can see from here, okay, it extends upwards, so parallel to this edge, which I already have. I can actually use just a bit of sliding set squares there again. So take the longest edge, it will give me the most accurate measurement, or reading I should say. So I'm going to extend this up a little bit here. Now that edge is going to go up, and at this one it's going to go up to there. So it goes up like that. The next one that gives me a height is this one here. So it's off of this guy. I'll use him next. And then the next one that gives me a height is this guy. I'll use him last. There. And just to be able to complete that then, I should realise then that I should have extended up my other ones, just to have them ready. So this guy here, I can see how far he's going to go over, so it's over to there somewhere. And likewise with this one, over there somewhere. And at this point now, they're just going to run parallel with this edge here. So it hits, you can see where it's hitting here and here. And we can see we've kind of got our 3 bars. So it's just a case of heavying in that. Okay, so there we have it. That is part A done. Complete the elevation. Okay, not too hard, nice and easy that one. Now what it's asking us to do is determine the true inclination of the diagonal AB to the horizontal plane. Okay, so what they're asking us is, we have a diagonal line here extending on the flip chart, along the flip chart actually, so it's on the surface of the flip chart, from the bottom left corner here A, up to the top corner here B. So we can see that A is on the ground and B has a height to it. So what we'll actually use here is the principle of a cone to actually help us out. So this, you'd have to just kind of understand the principle of a cone to be able to work this out, okay, and understanding how true lengths would work as well in relation to the vertical and horizontal planes. So what we need to do is, for any line to be a true length, you need it to be parallel to one of the principal planes in one view to make it a true length in the other. So what we could actually do is, you could do it 2 ways here. You could either from B, you could rotate A up, okay, until it, and extend out B and rotate A up until it comes out here, and then what we would do is project it down and then extend it across, and we'd be able to find it, okay. But the easiest way to do this is, if we treat B, okay, as the apex of a cone, okay, we know that when we look down at a cone in our plan view, we see it as a circle. So if we treat B as the center of a circle, or the center of a cone in this case, where A is on the ground and it's on the perimeter, I'm going to rotate from B, like this, rotate it around, and extend B across. Okay, and what I've essentially done there is I have rotated the position of A until it's in its new position. Oh, excuse me, right here. Okay, now the distance from B to A has stayed the exact same. B is the apex and A is on the ground, and all I've done is I've rotated A around, okay, until it's in this position here. That generator, I've just moved it into this position here. But what you can notice is that that line now, BA in its new position, is parallel with the XY line. Therefore, because it's parallel with the XY line, remember, my elevation is when a person is looking straight perpendicular to the vertical plane. I am now looking perpendicular to the line BA, okay, in its new position. Because I'm looking perpendicular to it, I can now see it as a true length in my elevation view. So, A was still at this height here, it was on the XY line, so it still remains on the XY line. So it's simply a case of where I've got it in its new position plan, project it up to its new position in elevation. I'll actually call it A1 in this case. I'll call this A1 there. I know it's a bit small just underneath the X there, apologies for that. And I will use a green. Probably should have used the green down here as well. Stuck with the colours that they had on the sheet. So put a green in there. So that line there, okay, is my new generator BA1, and I'm going to connect that over here. And what I've now got is actually the true length of the line BA1. Okay, true length line AB, or BA1, or whatever you want to call it. I'll stick with the line AB. But what they really want was the true inclination, and the true inclination is the angle inside there. So that angle, okay, whatever it is, certain degrees, I'll just put it in like that. If you have a protractor on the day, nothing wrong with coming along and measuring that. Just make sure I'm 100% accurate, right on it there. And that is reading for me 10, 20, 30, just short of 40. It's actually reading 39 degrees for me. Okay, but simply putting in that symbol on today will suffice absolutely fine as well. Okay, so a little bit on that there, guys, just using the principle of a cone to help us determine the true inclination by treating A as the, or B as the apex of the cone, and rotating A around until it is parallel with the parallel with the XY line in my horizontal plane, but therefore I'd see the angle in my vertical plane, okay, in my elevation view. Alright, so that was quite helpful there, guys. Now what we're going to do is we're going to move on to A3 at the top right of the page. Okay. Right, folks, so for this question, it says, question A3, the 3D graphic below shows a pencil in the form of a regular prism. When a conical top is applied to the pencil by the sharpener, it results in a series of hyperbolic curves near the top of the pencil as shown. So you can see here, obviously, they've kind of cut or topped the top of the pencil, okay, or sharpened it, and we've got these little bits here, okay, which are resulting in these hyperbolic curves, okay. It says the drawing on the right shows the axis A1, so we've got the axis here, A to A1. We've also got the directrix D to D1, and then a focus for one such hyperbola. The hyperbola has an eccentricity, okay, so this is important here, eccentricity of 3:2, okay. And part A, locate the position of the vertex and draw a portion of the hyperbola. Note, it is only necessary to draw one branch of the hyperbola. Hyperbolas usually occur as in double hyperbolae. Okay, so if you draw one, you can draw the mirror image on the opposite side, and they're only absent for one branch of it here, so that's okay. And then locate a point P on the curve, which is 60 millimeters from the focus, and construct a tangent to the curve at point P. So, these ones here, okay, not too bad, because we've been given our line of eccentricity and our measurement for that. Now, eccentricity is this, you usually use this method here. So our eccentricity is 3:2. So what that means is PF over PD is 3:2. So what that means is a point on the curve to the focus is 3 parts away, then that same point to the directrix, which is 2 parts away. So we're going to just use that kind of principle. So I could actually, if I just multiply that by 10, I could say that a point on the hyperbolic curve is 30 millimeters away from the focus in comparison to the same point, which is 20 millimeters away from the directrix. Okay, so we're going to use that principle to help us out here to find our line of eccentricity, which will then actually help us locate our vertex using some common principles to all conics. Okay, so from my focus, I'm going to actually do the 30 millimeters part first. So I'm just going to measure out 30 millimeters like this from the focus. Just going to mark 30 out here like that, and using my compass, okay, put my compass center point on the focus at 30 there. Just going to swing an arc here like that, and along that arc then, okay, from the directrix I'm going to measure out 20 millimeters. So 30 millimeters from the point to the focus, and 20 millimeters okay, so there's our point right there. That will actually help us determine our line of eccentricity. Okay, so I'm going to put that line of eccentricity in put it in green. That line is very important there. That is our line of eccentricity. I'm just going to write in L-O-E, line of eccentricity. Okay, and what that essentially means is this curve, this arc, was 30 millimeters away from the focus. So somewhere along that arc was a point that was 30 millimeters away from the focus, and then what I did was I measured out 20 millimeters from the directrix, and where that 20 millimeter line cut through the arc, that gave me a point on my line of eccentricity. Okay, and that there determined it. Now what we're going to do is get our vertex. So by projecting at an angle of 45 degrees from your focus to hit the line of eccentricity, where that 45 degree angle hits the line of eccentricity, project down perpendicular to your axis, that will give you your vertex. Is very helpful. And what I'm also going to draw on now is my focal line. So the focal line up here, put it down as well, and with my focal line there, put that in a little bit darker actually, sorry, seeing how it's coming up on the screen. With my focal line dot, what I'm going to do now is I'm going to do a series of lines here to help me determine points. Do one more. Okay, doesn't really matter how many you do and how spaced they are. So, where each one of these lines I did hits my line of eccentricity, I'm going to extend it across to my focal line. Probably didn't need that one at the top, but sure, put it in. I extend it on my focal line there, and where this one hits here on the inside, I'm just going to extend it across that way. Now, how we actually get the points and get points on our hyperbolic curve is put your compass on the focus, okay, and where each one hits the focal line, or sorry, the line of eccentricity I extended across, going to bring it across to where it's on the focal line, and rotate down like that. That helps me determine a point there. As you can see, this one's gone off the page, so that doesn't matter. Just use the top half of the curve and put them in on the bottom half when they appear on the page. this one is hidden here now. Perfect. And that next one right here, it's just hidden inside just a little bit. There we go. And the focus point where it hits the line, focal line where it hits the line of eccentricity actually gives me a point. So I'll find that on the opposite side. And this one is just going to work backwards. So when it's in between the focus and the vertex, you across and you just work backwards. I'm using pens here, so they're probably not as accurate. There we go. Okay, so just locating those points. Got a point here, a point right there, point, 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 point. So I'll sketch that in quickly. Okay, so there we have the hyperbolic curve, guys, by using the line of eccentricity. Okay, we can see it there on the eraser that they gave us. Now it's saying part B, locate a point P on the curve which is 60 millimeters from the focus. Okay, so that's easy enough. We can find that point P easily enough. So just using my compass here, I'm going to measure a distance of 60 millimeters. So I'm happy with that. So from the focus, I'm going to go up to the top half of the curve, swing an arc of 60 there, so that's my point P right here, call that P there, and from the which is 60 millimeters from the focus, and construct a tangent to the curve at point P. Okay, so principal common to all tangents, I'm going to connect F to P. Okay, and perpendicular to that line, F to P, what I can do is, I'll put my square here on the line. I'm going to rotate it so that I've created a perpendicular angle to this line F to P. So that angle in there is perpendicular. Where that point hits the directrix, should give me tangent. Hopefully it does. And there we have it. That there is my tangent. That is a principle common to all conics. Okay, so if you extend the focus out to the point and then go perpendicular from that line, from the focus to where it hits the directrix, okay, that point where it hits the directrix, if you connect that to P, that will give you your tangent. Okay, so that part not too bad either. There is other ways about that, where if I was to extend my line of eccentricity, I'm just thinking, I'm trying to remember this one, and extend it out perpendicular, so if I extended out my line of eccentricity like that, and I went perpendicular, so 45 degrees that way, I'm just thinking that would have gone out like that. That gives me the focus at the opposite side. I could find the vertex here, so I'll just do it anyway just to explain. Okay, so that's actually completed there. I wouldn't usually do it this way, but it's just good for demonstration purposes. So I could extend out my line of eccentricity. Remember I said it was a double hyperbola, so I could extend out my line of eccentricity just going the opposite way. Just make sure that's accurate there. Yeah, I'm happy with that. And if we look at this line here, how I found the vertex originally by projecting from my focus at an angle of 45 degrees, I could also do the same. I could go down at 45 degrees as well from my focus here. Okay, where that hits the line of eccentricity will actually show me, oops, let me go right there, where my, extend this out lightly, ever so lightly, vertex is on my double hyperbola at the opposite side. So if that's V, for the sake of it, we'll call this V1. Okay, and you have to remember your vertex is here, so I'm just thinking directrix is here, so my focus will be in the opposite side. Okay, so I can take the distance to my focus on my compass, take that distance there on my compass, I can mark it out on the opposite side. And as I said, if that's F, then this will be F1. And what you could do then is you could connect F1 to P, like that, like I've connected F to P, and hopefully my accuracy works out. What I could do then is I could bisect the angle between FP, F1. And we'll see how it works out. Be a good test of accuracy regardless. That doesn't look too bad. So at that point there, P, hopefully the line will continue on, and you can see if I stay extended on, it goes right to it as well. So my accuracy is working out quite well there. That second one, okay guys, is probably a little bit harder to understand, okay, by extending out your line of eccentricity and going perpendicular. So 45 and 45, that angle in there is perpendicular, okay, down here, and that would actually just help me find the vertex at the opposite side. By finding the vertex, I can then find the focus, and focus to point, bisect the angle, also gives you a tangent. Okay, hope you found that helpful, guys. What we're going to move on to now is the last question on this page, which is question A4. It's at the bottom of the page. Alright. So this question, guys, A4, it says the image below shows the atomium structure in Brussels, which is based on an inclined cube. Okay, so we can see obviously the cube as it's resting, one corner of it, okay, is obviously resting, looking at the auxiliary here on the ground. The drawing on the right shows the incomplete projections of a similar inclined cube. Part A, complete the elevation of the cube, and part B, draw the plan and elevation of the smallest possible sphere that would contain the cube. Okay, just want to underline that bit there, contain the cube. It's not inside, so the cube, the sphere isn't inside, the sphere is on the outside, and the cube is on the inside of the sphere. Okay, so part A first, complete the elevation. Right. So just looking at this here and trying to identify the surfaces, cube is going to have 1, 2, 3, 4, 8 points or 8 corners essentially. So if I was just to call them with letters, I'm going to call this A here, then I'm going to say B, this corner here is C, D, go likewise at the top, E, F, G and H. So if I was to locate them, A is here, so sorry, technically these would be A1, B1, D1, C1. I always say 1 because you use an X1, Y1, so you go with the corresponding letters then, A1, B1, so on. So then we'd have A here, B was at the back, so I'm just thinking, yeah, D is at the front, so I'd have D here, B here, C is on the ground, so it's inside, okay. And then E is at the top, okay, so just looking here, I'd assume this is going to be E up here, then F, G and H. Okay, so we can see A connects to B, B to C, C to D, D to A is up to E, B is up to F, E up to G and D up to H, and then obviously we've got E, F, G, H as well. Okay. Just to get your understanding, okay, labeling is very important because sometimes people might look at this and actually think it was a hexagonal based prism and so forth. Obviously we know looking here it's not, but you just have to be able to work your way around an object, okay, so labeling is very, very helpful in that case. So now it's a case, just I'm going to project back my lines, my vertical heights, just have these done. So using a bit of sliding set squares here. So they've already projected back A, B, C and D for us. So now just to make sure E is lined up. So there we have E, F and H. See they're going through there fine. And then finally G. Okay, and that will just help us determine the vertical heights for them when we're using them in the elevation up here. So just to find those, I can locate just to find those. Bit of orthographic projection here. I have the points in plan. Let's find them in elevation. So C is already given to us. So there's C right there. Okay. Because C is on the ground. Okay, B and D are the next height up, so I'm going to work up them next. So that'll be B right there. Okay, now I want to find D. I imagine that's actually D there, which is the same height as B. Yep, so that's D there, right there. And now I want to find A. So A is up here somewhere, and all I want to do is take the vertical height of that. Remember, project on the plan, take your heights from the elevation. Likewise, we have the plan, we have the auxiliary, so I can take the heights from the auxiliary to work back to my elevation. So take that height, mark it up, and that there will give me A. And I know when I'm looking in this direction, because it's tilted, I am going to see the face A, B, C and D. So I can heavy in all of that. Imagine that would be parallel. Yeah. So I've got that face there. Okay. Now I will see that face A, B, C and D. I also might see the face A, E, H, D when I'm looking in this direction. I do think I will see that. So what did I say? A to E to H to D. Okay, I think I'll see that as well. So locate those. A to E. So I'll find E, which is directly above C somewhere. And I said H and D as well, so I need to find H too. So likewise with E, take the vertical height from E1. It's going to be somewhere up here. I have to extend it up a bit further, and it was the same with H. There, so make sure I get the right height. There's H there, and extend this one up further. So that'll be my E and H. Just put it lightly, just want to be certain. Yeah, it's starting to kind of come together now. Yeah, I think I'm on the right track. Yes, I can heavy in that. And the other face then that I'll obviously see then is the face C, D, H. I'm just following it here. So it'll be C, D, H, G as well. Okay, so we've kind of got the letters A, B, C, D. Yeah, I haven't found F yet, so I'll get the back. Okay, so I'll find G next. G is going to be up here somewhere. And once again, take the vertical height. There's a bit of working out in this one. Nice question if you've kind of got good visualization skills. So there's G, and once again, I'd imagine it would probably be parallel to the edge. DH there from C. Seems to be working out fine as well. So there's our cube in the elevation. However, we obviously have to put in the hidden detail. So I do have one more point to find there. I've got A, B, C, D. A, B, C, D. I've got E, so I have to find F as well. So F is going to be somewhere there. And F is at the same height as H. So rather than taking the height again, I could just project H across, because I can see the height was here. So H was at this height there. So F is also at that height. So now I've got F here. And to complete the faces then, I've got all the kind of ones that I have seen. Okay, so I see the face A, B, C and D when I'm looking in this direction. I also would see the face A, D, H, E, and then the other face we see was C, D, H, G. So C, D, H, G. So the faces at the back, I'll have A, B, F, E. So you see it here, A, B, F down to E. So that face there. Put that in hidden detail as best I can. And then to complete the structure, F will also connect to G. Yep. Okay, so there we have our cube in our elevation done. Okay, that's part A done. Now the last part of the question says, draw the plan and elevation of the smallest possible sphere that would contain the cube. Okay, so essentially I'm actually going to use this little graphic here to actually be quite helpful to us. You can see here, if you look at the balls, okay, there's obviously one behind this connecting on the lower surface. Okay, so if I just imagine there's one in there as well, connecting this guy to this guy to this guy to this guy as well. Okay, so we've kind of got the A corners as I previously said. Now what we want to do is we want to draw a sphere that will actually contain the cube. Okay, so the cube is inside and obviously it's going to be touching certain corners for it to contain within it at the smallest kind of size. Generally how that would work is a cube that contains, not within but around, sorry, a cube that is contained within a sphere. The center of it will be, if I was to connect opposite diagonals. Okay, so you can see here, this is kind of the top surface. Okay, these four cubes. Okay, actually put letters on them again. A, B, C. I'm going to call this one D. And then down the bottom I'm going to have E. So this guy, the dark guy, which is at the back, I said, I'm going to say he's F. Then I've got G and H again. Okay, hopefully you can see that there. It's not too bad. Alright, so A, B, C, D, then lower surface E, F, G and H. Now essentially the diagonals are connected, okay, and it's the opposite diagonal. So C technically would connect, which is on the top surface, to E down here. Okay, likewise A will connect to G, okay, same with B connecting to H, okay, and D, which is on the top surface, will connect to F at the bottom, okay, and that would be seen as a point. But what you can actually see there is that every one of them goes through the center, okay, and essentially then it's a case of the center to the furthest diagonal, which is, we'd see it here as C or whatever it is, B, depending on how you see it in what view. That would help us draw a sphere that would contain the cube. So that's what we have to do. We have to identify the longest diagonal essentially. So if I take, let's say, the face here, A, B, C, D, okay, so I've got A, B, C, D, I can see if I look here at my, say, auxiliary view here, if I connected A to G, okay, or A1 to G1 in this case, that is a long diagonal. So that's what I'm going to do. I'm going to connect A there to G. Oh, sorry, lifting off the set square there. Poor drawing technique. But anyway, A to G is connected there, so that's one long diagonal connected. Another one then would have been E to, I'm just thinking, is it E to C? Yeah, so another one there, you can actually see it here, it's already drawn. E to C is already drawn. So how that would appear here is a line like this. E to C. Oh yeah, it's actually already drawn, it's right there. Apologies. So right there is technically the middle of our cube, okay, in our elevation view. Now what we have to just determine is, since we have the center, okay, all we have to do to determine is, and I'm going to put this in, and I'm going to imagine the radius is going to be from the center to E. If I just think of joining diagonals and think, let me see, B will connect to H by the looks of it. So B to H would be this one. And I'll imagine, hopefully it goes through the middle as well, and you can see there it does again. And it's a case then, so I've got that one, and then D would also connect to F by the looks of it as well. You can see once again it's going through the middle. So we know we're on the right path there. Now it's just a case of working out which one is our longest diagonal to be able to draw it in. So if I was to connect it to F, okay, even though that diagonal in reality is the same as every other diagonal with inside it, we can see if I draw that in, that's not going to be correct, because no way does that contain the cube. If I put it out to A, same thing. You can see here, no way does it contain the cube if I was to draw that in. Now if I draw it out to B, we probably have more of a chance with this one, so I'll just see. But look, you can see it's just falling inside E there, and most likely C, yes. Whereas if I connect it out to E here, and hopefully that'll be the same distance to C, yes it is. There is a sphere, a sphere that contains the cube. Okay, and all we had to do was we had to search for the longest diagonal. So with the center point right here as well, I'll be able to draw that in my plan view. So a little bit of understanding in that. Nice little question there. And if I wanted, I could draw it up here in my auxiliary. Might as well. I have the radius. Hopefully it works out. As I said, I'm just trying to remember A connected to G. So just to make sure I got the right center, yeah, it's going to be right in there as well. So using the same, hopefully this works out. Yeah, it seems to be. I'll put it in lightly first. Yeah, there's our sphere. Whoops, slipped off there a little bit, sorry. Now, I don't think I had to draw it in the auxiliary. Probably drawing it in the elevation and the plan would have sufficed. But it's still just nice to represent it and show our understanding. Okay, so there we have it, guys. That is a cube that is contained within a sphere, okay, by connecting the longest diagonals and finding the center of them, okay. That is question A4 done, guys, and from the 2016 higher level that was. Hope found those questions helpful. That's them complete.